Okay, so I've got here 4 rates of change questions. So we'll see how these goes. If there's some more issues as we go through, we can do some more examples. But we'll see how it goes, and then we'll move on to the next thing that was voted on was inverse functions, then continuity, then it was approximating errors, and the last thing was the tangents and normals. Okay, so we'll start from the top and see how things go. Okay, number 1. Okay, if a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rates. So that's your keyword, right? There's rate or rates of change or something like that. So find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay, so we have our word problem. Let's go through it, draw a little picture, and then we'll set up the equations. So it's a snowball, right? That thing's round, so let's draw a little picture of that. So we've got ourselves a snowball. Its surface area decreases at a rate of that. So we know what the surface area of a sphere is. What will that be? Good. Okay, so we know that's going to be the surface area. Find the rate at which the diameter decreases when the diameter is 10 centimeters. So here we're looking at the diameter, but our formula we wrote there, that's in terms of the radius. So we need to do a little bit of manipulation there. So that's not so bad. We know that the diameter is just twice the radius. So if we want to write this in terms of the diameter, yeah, good. Okay, so this is going to be, we get a quarter from there, take that out, so we get pi times the diameter squared. Okay, so we got everything here in terms of the diameter, which is good. Now we want the rate of change of this. Okay, so we've got S, remember that is S in terms of T, because it's decreasing, and D, that is also D in terms of T. Okay, you don't need to write it like that, but that's how we know. Right, it's implicit. Okay, we don't need to write it. So we do d by dt on both sides. Yeah, so d by dt, d squared. So this will be 2 pi d by dt. Yeah, so that's just using the chain rule, and we know that d is a function of time implicitly. Okay, so we have our equation. We know what is known and what is not known. So ds by dt, we know that. The rate of change of the surface area is 1 centimeter squared per minute. So this we know. The diameter, we know, 10 centimeters. The question is asking for the rate of change of the diameter. So we want this over here. Okay, a little bit of rearranging, and we have our answer. Okay, quick check. It's negative. That means it's decreasing. Of course, if it's melting, obviously it needs to be getting smaller. And then the units, the diameter was given in centimeters, so centimeters. And then the time, it says it melts over minutes. Okay, so then the units here will be centimeters per minute. Remember, the final answer is always like 2 marks, 1 for the number, 1 for the units. Okay, whatever units were given in the question. Okay, you can either leave your answer like this, or like I said before, 2 decimal places, that's fine. Otherwise, just leave it like this. Okay, any questions with this first one? Okay, please remember, you're not coming to me afterwards with questions. You ask now or forever hold your peace. Any questions? Yes.
Like 3 steps from the bottom.
3 steps from the bottom. This one. Yeah. So on the left here is just the derivative of the surface area, so ds by dt. On the right here, we know that this d is a function of time implicitly. It's implicit. We don't write it d of t, but you can write it like that. So we've got a function on the inside and a function on the outside. As soon as you're saying f of g, you need the chain rule. So by the chain rule, the derivative of the outside, you take the 2 down. We did that over here. And then the derivative of the inside is d by dt. It's just chain rule. Okay. If you do want to write it explicitly like this, that's perfectly fine. But it's not needed. You just want to write it like this, that's fine. Okay. Maybe it's safer if you write it like this. Okay. Any other questions? Oh, good. Okay. Let's have a look at number 2. Again, all of these will be some word problem. Okay, 2 cars start moving from the same points. Okay. 1 travels south. Okay, at 30 kilometers per hour. Right, already you're seeing rates of change, right? Kilometers per hour. That gives you your hints. And the other travels west at 72 kilometers per hour. Okay, at what rates is the distance between the cars increasing 2 hours later? So functionally, this is exactly the same as the revision quiz, the one with the cyclist and that balloon. So a cyclist is going one way, balloon's going the other way. Find the rates of change of the distance between them. Right? It's exactly the same. So the picture is the same, the working's the same, it's just worded differently. So when it comes to tests and so on, you might get a different word problem, but it could be exactly the same problem. For example, like you have that cone, right, with the water leaking out. If it's a cone or if it's a pyramid, it's exactly the same problem, right? You got some volume, it's changing. Whether it's a cone or a cube or a pyramid, the working is exactly the same. Same thing with this. It looks entirely different to the cyclist problem from yesterday, but it's the same thing. You draw a picture, you see both of them is just a triangle. Okay, where the side lengths change. So please keep that in mind. If you've done one problem in the tutorial, don't just memorize the word problem and the answer. Look at how you solved it. Because the way you solved it yesterday is exactly how you solve this today. Okay, so let's draw a picture of this. So we have some starting points. Let's just say over there. One of the cars goes south. So it's going to go down like that. And another one is going to go west. So something like that. And we want to know the rates of change of the distance between them. Well, if you got a car over here and a car over here, let's say S over there is the distance between them. It's a right angle triangle. This is exactly the same as what we had with that balloon. There was a balloon rising up. There was a cyclist going this way. Find the rate of change of the distance between them. I mean, it's exactly the same. This triangle is just upside down. Same problem. So again, don't memorize the problem. Look at how you solved it. Let's put some variables here. So horizontally, let's just call that X. Vertical, let's call that Y. It's a right angle triangle. So we know that that hypotenuse squared is just X squared plus Y squared. Now you could do the roots on both sides. Let's just leave it like this. What do we want? We want the rate of change of the distance between them. We want ds by dt. So there's s over there. We want ds by dt. So let's do d by dt on both sides. Okay, if you did this yesterday, you should be happy. You got part mark so far. So d by dt, s is a function of time implicitly, x is a function of time implicitly, and so is y. So when we're doing the derivatives, we need to remember the chain rule for each of those. So here we're going to have 2s ds by dt. Here we're going to have 2x, not just x, dx by dt, because it's actually a function of time. And 2y dy by dt. Again, it's a function of time. Quick simplifying, we've got 2's throughout there. Let's get rid of those. Okay, so we've got s ds by dt is equal to x dx by dt plus y dy by dt. Again, always think about what do we want? We want the rate of change of the distance between them. That's the ds by dt. We got this s in front here, so let's divide that on the other side. Okay. And those that did the catch-up have the same formula. So 3 different problems, exactly the same method to solve it. Okay. Now let's see what we know, what we don't know. So ds by dt, we don't know that, so we keep it on one side. Now on the other side, we need to see what do we know, what do we not know, and then we substitute. So dx by dt, that's the speed of this car over here, right? The one going west. Do we know that? Yes. Okay, so that's fine. dy by dt, that's this car going down here. Do we know that? Yep, we got that over there. What about x and y? We don't know what that is. We know the speeds, but we don't know the distance. But what we're given here is the speed and the time. Or if I give you speed and time, you can work out distance. So let's do that. So law of side working. So we want the distance. So that's the speed times the time. So the x, that was the car going west. So let's not mix things up here. So the one going west was 72 for 2 hours. So how far did he go? Well, 72 times 2. What do we get for that? 144. Good. 144 what? Kilometers. Okay. And then y, very similar. That's the vertical one. So that was 30 kilometers per hour for 2 hours. So speed times time. Yeah, 60. Okay, so let's just substitute. Now we know all of these. Do we? No. What's missing? S. But we know how we can find S from here. So S equals the root of x squared plus y squared. We know what those are. We just worked them out. And now we just substitute. Go. So you sub in, and we get the rates of change of the distance. Okay, S, that was a distance, so that's going to be kilometers. T, that's the time, that was in hours, so kilometers per hour. Okay, you fill in the number there. Right. Any questions for this one? Yeah.
So I saw that if you if you sub in the rate of change in the next direction and the rate of change in the right direction, the Pythagoras figure, you get the same answer. Then you don't distinguish that.
The rates of change in?
And like the x plane and the y, like the speed in the x plane and the y.
So that works here. So we'll do that here. So let's say you've got a velocity vector v. Don't write this down. So you've got some velocity vector v. You know, there's some speed in the x, speed in the y. And then that means that the length of that is root, vx squared plus y squared. So you can do it like that. That only works if it's constant. If it's constant, then you just scale the velocity by the time. That gives you the speed. So we can see it like this. Right? So we got the speed in the x direction times the time. That's the distance. And for the other one, it's the speed in the y direction times the time. But here, because it was constant, it's just speed times time. So this can come out. You end up with that. That's how it works. If it's not constant, you can't just take the t out. For example, if they're accelerating, it's not vxt. It's vxt plus half a t squared. It won't do that anymore. Okay. So just be careful with that. Okay, yeah, that's why it works. So you just take the t out, you get the same thing. Okay, but careful, that only works for constant speeds. Right. Any other questions? No, good. Okay. Next one, the 3. Okay, a cart's 50 meters above the ground. Moves horizontally. At a speed of 2 meters per second. At what rates is the angle between the string and the horizontal? When 100 meters of string has been let out. Okay. Now this one looks completely different to the other problem. We see here, this one, there's a car moving west, a car moving south. What's the rates of change of the distance between them? Right? That has nothing to do with flying carts, but we'll see it's pretty much exactly the same. So again, do not memorize the problem. Look at how you solve the problem. So let's start with the picture, and then we'll see these are pretty much the same problem. So we've got a cart above the ground. So let's draw in the ground. We've got some cart here. Let's put it as a dot. And it's going to be moving horizontally at a speed of 2 meters per second. Okay, so it starts over there. It's moving along at 2 meters per second. At what rate is the angle between the string and the horizontal when 100 meters of string has been let out? So let's say it starts at that first point. It's going to move to the second point sometime later. Let's say the string is like this. Okay, you over there, you got the string. We want to know what is the rate of change of this angle between the string and the horizontal. So we've got the string there, we've got the horizontal there, so this must be the angle. Make sense? Okay. You call it angle of inclination or whatever it's called, but that's the angle. When 100 meters of string has been let out. Well, that dotted line is the string, so it must be 100 meters. All right, that's our picture. And if we just connect the last line there, going down, we have ourselves a right angle triangle, exactly the same as what we had before. So again, the method before using Pythag, doing the derivative, it's exactly the same. So the working is the same, even though the problem is completely different. Okay, so let's redraw this, put in our variables, see what we need. Okay, so at what rate is the angle between the string and the horizontal? So we've got x and y, and some angle over here, theta. So there's going to be some trig involved, because x and y, we know what those are, or we can work out what those are, but that theta we need to figure out. So if this is theta over here, what other angle in our triangle is also theta? Top one. Good. Why? Because these are parallel, alternate angles. Okay, so that one's theta. So if we have x and y, we want the rate of change of theta. We can relate these now. What can we do to relate them? 10, yeah. Tan theta will be what in terms of those sides? Y of x, opposite over adjacent. Yeah, good. That's all we need, right? So we've got this. We want the rate of change of the angle. There's the angle inside tan. We want d theta by dt. Let's just do the time derivative on both sides. Exactly the same as what we did with the Pythag. We did time derivative on both sides. Okay, now I'm not writing of theta, of t for all of these, but we know. Theta is a function of time. X is a function of time. What about y? It's a constant. How do we know that? Moves horizontally. It says nothing about moving vertically, so y is fixed. Moves horizontally. Okay. So let's do the derivatives. Derivative of tan. It's x squared. But we're not done because theta is a function of time. So by the chain rule, d theta by dt. Now the other side. Y is a constant. We can forget about that. So we're doing the derivative with x there. And then dx by dt. Again, the chain rule. Yeah, we end up with that. Everyone clear? Okay. Now again, we want d theta by dt. That's the goal. So let's keep that on one side, put everything else on the other, and see what we know and what we don't know. Yeah. So we have everything else on the other side. Now we see, are we given the value or do we need to calculate it? So let's go through. So y, are we given that? Yeah, cut 50 meters above the ground. That's the height y. Okay, so that's fine. Dx by dt. Yep. Horizontal speed, so that's dx by dt, is 2. So we know that one. X. Do we know x? Is that given to us? No. No. X is not given to us. And theta? No, that's not given to us. So x and theta, we need to do some side working to figure those out. Okay, let's redraw our triangle and figure those out. Okay, what's this hypotenuse over here? That's 100. Right? Remember this. When we abstracted this to a triangle, remember that was the string. That was 100. What about this y? 50, yeah. Can we calculate x now? Yeah. Okay, so x must be the root of 100 squared minus 50 squared. What's that? Sorry? 50. Like that. Okay. So we've got x. Okay, good. So top part's done. Now theta. Well, there's theta over there. And now we know what x is, so we can put that in. Now pick your favorite trig ratio. What's theta going to be? Sorry? Yeah, we can use 10. That's fine. So what's theta? Remember radians, please, not degrees. Yeah. Yeah, you can use any method. You can use whatever you want. Yeah, you can use sec squared. So that's going to be hypotenuse over adjacent. Yeah. So what will that be? 0.52. Okay. Sorry? 1/6 pi. Like that. Okay. So yeah, you can find theta like that using the trig ratio. Or like you said there, we can use the side length here for the sec ratio. So sec theta. Remember, we need sec for that. So sec is going to be hypotenuse over adjacent. And we want sec squared, so we squared. Okay. Either way, you can solve for theta, then substitute, or you can use the ratio for sec. Okay, you'll get the same thing. And then once you're done with that, you just substitute in, you got your answer. And then this was 100. Okay. All right, you got your calculators, you can simplify that there. So this will be whatever you get, radians per second. Okay, remember theta, we work in radians, not degrees. Okay, and again, you see, same sort of thing, right? You draw your picture, you got your triangle. What do we want? What do we need to work out? It's the same idea. Okay, any questions for this one? Yeah. Process, yeah. Probably about the same. Yeah. Yeah, it's about the same. If you can draw a triangle and you can find the missing side, you fine for the test.
Yeah. When you derive over, how did you get x to it?
So this x over here is secretly an x to the minus 1. So when you do the derivative, it's minus in front, x to the minus 2. That makes it squared. Okay. Yep. Y was a constant. Oh, over here. So the kite is 50 meters above the ground and moves horizontally. If something is moving horizontally, it's not moving up. If it's not moving up, y is constant. So it's only the x that's changing because it's going horizontally. Yeah. Maybe for the June test, it's going horizontally and vertically. Yeah. But here, it's just moving horizontally. All right. Any other questions? Okay. We've got one more here. Okay. If two resistors R1 and R2 are connected in parallel. Sorry? Another example. Sorry? In the tut. Yeah? I wonder why we're going through it again. Maybe some form of emphasis. I don't know. Maybe these are important for some reason. Okay, if two resistors, R1 and R2, are connected in parallel. Yeah, the reason I'm doing it again is because about a third of the class haven't opened the tutorials. Remember on Learn, I went through it with the second years. I can track exactly what you've been doing. So something like this. I won't point out any names. I'll just show you. Actually, let's do it with the second years. Then there's no issue. Just don't tell them. So you go here to reports. Let's put here activity report. So this is everything. Let's say homework solutions. Second year homework solutions. Over here, 21 views. I've got a class of 62 for the second years, and this tells me that 21 have opened them. We did class test revision recently, and only 2 have opened them. Yeah, it's interesting. We go through here, tutorial solutions, 41. Again, I got a class of 62, so I don't know what the others are doing. Over here, solutions 32. So, I mean, I can see what you guys are doing. And I can even do something like this. Logs or participants. I can choose someone, and it shows me exactly what time you opened each thing. And if you have opened it. So let's say, no. No, let's pick someone else here. That's the tutor. Let's see. Yeah, it gives me a whole thing here. Every single time you logged in, whatever you've been doing, there we go. He opened extra integration at this time on this day. So I can see what you've been doing. So with you guys, with the tutorials, it's about like a third of the class have been going through the tutorials and the solutions. I mean, I can't open it for you. If you're going to do the work, I mean, that's on you. Yeah, so when you see me do the tutorial questions again, it's because of the third of the class are seeing it for the first time. Okay. So if two resistors, R1 and R2, are connected in parallel, then the total resistance is given by, so we know what it is from physics, but I'll give you the formula here. So we have 1 over R is 1 over R1 plus 1 over R2. Just a note, right? You know this from physics, right? But for the math test and stuff, if there's equations like this, I'll give you the equations. Like the quiz we did with that ideal gas, right? Everyone knows it, but you're given it anyway. Same thing with this. So everyone knows it, but it will be part of the question. Okay, so we've got that. And we know a few things. So R1 is increasing at a rate of 0.3 ohms per second. Yeah, the units you need to know, right? Ohms, you have to know what that is. Okay, R2 is increasing at a rate of 0.2 ohms per second. Okay, what is the rate of change of R? So that's the total resistance, R. When R1 is 80 ohms and R2 is 100 ohms. So here we don't have to come up with the equation like we did with that Pythag and the triangles and all of that. Here it's given. We know R1 is changing, R2 is changing. How is R changing? Okay, so we have this. We want to know how it's changing. So d by dt on both sides. It's always the same. So same thing as before, d by dt here. So it's going to be minus 1 over r squared dr by dt, which is what we want. Yeah, that's the goal. And then these other ones, both of these are changing. So it's going to be minus 1 over r1 squared dr1 by dt minus 1 over r2 squared dr2 by dt. Now, before we make any sign mistakes, let's cancel out the minus ones there. And then we can take r squared over to the other side. So we have everything on the one side. dr dt, that's what we want. Now we need to ask ourselves what's given and what do we need to work out. So R1, yeah, we know what that is. Okay, R2, yeah, we know what that one is. dr1 by dt, we know what that is. dr2 by dt, we know what that is. But this over here, we don't know. Yeah, we don't know what that is. But that's fine, we can work it out. We know the equation. So do a little bit of side working. Yeah, sorry, 1 over r. So this is going to be 1 over r1, which we know is 80. And 1 over r2, which we know is 100. What do we get? (44,44). Okay, quick check. Remember, if it's in parallel, this is always less than the smallest resistor. So if you get something larger than 80, you've done something wrong. Did you know that? You didn't know that? No. What are they teaching you? Okay, please make a note of that. If you want to check your answer, this should always be smaller than the smallest resistor. If this ends up being larger, you've made a oopsie somewhere. You really didn't go through that.
No.
Do you know how to get this formula? Derive the formula from the voltage splitting.
Oh.
No. Hey. Okay. Just as a little bit of advice for later on, in physics, you're going to have deriving formulas later on, right? Wave equation, derivations, and so on. Please make sure you know how to derive things, right? You got, equation 1, 2, and 3, derive equation 4. Please make sure you know how to do that. Okay, so dr by dt, r squared, we just worked that out. Okay, 1 over r1. Okay, dr1 by dt, we know what that is, 0.3. Okay. Again, you got your calculators, you can simplify that. And then the units, so resistance, that's in ohms. T, let's see what that was. Right, we said here ohms per second. So units is ohms per second. Okay, again, please do not leave out your units. It's 1 mark, right? You put your units, you get your mark. Right. Any questions for this last one? Yeah.
So the 44 square.
Yes, sorry. It's great. Yeah. Thanks. Right. Anything else? Yep. Oh, the negative signs. So here we got -1, -1, -1. Times through by -1. You get rid of the negative signs. Yeah. And then this r squared over here, you just take over to the other side. Okay. Anything else? Okay. Okay. Let's see what the next thing was. I didn't really want to start this today. We can have a vote. So the next highest voted thing was composition and inverses. So we're just going through the list here. There's 23 votes for that. Either we spend another half an hour-ish going through that, or we save it for tomorrow. Okay. Who wants to go through it now? Hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Remember, we have a fixed amount of time. After Thursday, done, right? So, do you want to carry on now or save it for tomorrow? Okay, let's do another vote. Who wants to carry on with the other work? Okay, let's go. Okay, remember, right, it's up to you, right? You want to carry on with tomorrow, that's fine with me. This is your revision work, not mine. Yeah. No, we still have the lecture tomorrow. The question was, do you want to do this tomorrow or not? Yeah, no, tomorrow is still happening, please. If you don't want a lecture tomorrow, that's fine, but I mean, I'd rather do the revision work. So the next thing was composition and inverses. So number 1, given f and g, that talking needs to stop. Okay, if I can hear you talking from here, then they can also hear you talking. Okay, find f of g and g of f. Okay, so we're given 2 functions. We either put g inside f or we put f inside g. Okay, so number 1, we've got f of x is equal to root x plus 1. G of x is equal to sine squared x. Okay, so we want to do the composition. So the first one, f of g, we can rewrite it in a form that we know a bit better. So f of g of x is f, and then inside f is g. F of g. So remember where this g is going. That was the placeholder for x. Right? We had f of x. We place it there. So inside f, wherever we see the x, we now put g. Yeah, so we have that. Now you may or may not be able to simplify further. If it's just a single question on this, just leave it like that. If there's follow-up questions, like find the range and domain, then I suggest you simplify. Okay, it makes it a bit easier for the follow-up questions. But here, there's no follow-up, so we can leave it like that. Okay, now g of f. So there was x there. So g is sine squared x, and in place of x, we're now putting f. Yeah. And again, there might be some follow-up question. What's the domain? What's the range? Something like that. Or show that it's the inverse, right? So if this was the inverse, then you'd have some cancellation. You just have x. Okay, if these were inverses. But we're going to see that later. Right. Any questions for this first one? Okay. Let's say 2 more, and then we'll go into inverses. Okay. So f of g. Okay, so we're taking f. In place of x, we now put g. Okay, and then domain range. You know how to do that, yeah. Okay, and g of f. Okay, so here we've got x. We need to put the natural log. Any questions for this one? No, good. Okay, let's do one more. Okay, so g is 1 over 1 plus x. Okay, again, f of g, g of f. Let's see what these are. Okay, so in place of x, we're going to put g. Okay, and again, in place of x, we'll put f. Yeah, there might be some follow-on questions like domain, range, something like that. All right. Any questions for this? Okay. Okay. Let's have a look at the next parts, the inverses. Okay. Find f inverse for the following. Okay, so number 1, we have f of x is equal to the natural log of x squared plus 1, where x is greater than or equal to, greater than or equal to 0. Okay, so we've got the function, we've got the domain. Right, I could ask you what's the range for this, but here we just want to find the inverse. So we're going to call f y, and then do the inverse by solving for x. Okay, right, because the idea is f inverse of y must be x. Okay, so we've got the natural log there. We want to get rid of that so we can solve for x. So let's do the exponential on both sides. Okay, then we can take the 1 over to the other side. Okay, then we do the roots. So roots will give us some plus minus solution. Now we need to pick. Do we take the plus or do we take the minus? So this is x, right? That's our f inverse. Which one do we pick? The plus, right. The domain here was positive x. There we go. That's our inverse. Right. Any questions for this first one? Oh, good. Okay. Number 2. Okay, so we've got our function, we've got our domain. It's everything smaller than minus 1. We want to find the inverse. So we're going to let f be y and then solve for x. Okay, we want to solve for x, so let's take everything over to one side. Again, we still want to solve for x, so quadratic formula. Okay, so we have x is equal to minus 2 over 2, so we just have minus 1. Then the 4 we can take out, so that's going to be just a 1. Now we need to pick plus or minus. Minus, yeah, because we want x to be less than minus 1. Any questions for this one? Yeah. Denominator here. Oh, yeah, yeah. So the minus 2 over 2 is minus 1. And then here the 4, root 4 is 2. 2 over 2 is a, well, you can put a 1 there if you want. There's 1. Okay. Any other questions? Okay. Let's have a look at another one. Okay, so we got our function, got our domain. Again, I could ask you, what's the range? But here we just want the inverse. So let's do that. So we're going to call our function y, and we want the inverse, so we want x instead of y. The exponential is getting in our way from solving for x. So let's do the natural log on both sides. Okay, so that will clear out the exponential. So we just have minus x squared. Okay. Again, we still want x, so let's take the minus over to the other side. Then we want x, so let's do the roots, and we get a plus minus from the roots. Now we can't have two answers, right? It needs to be a proper function, so plus or minus, we need to decide. Which one will it be? Positive, yeah. Right from the domain, we wanted it to be positive. So this must be our inverse. Okay. You don't have to write the plus, right? That's just to emphasize we picked the plus there. Okay. Any questions for this one? Oh, good. Okay, got one more here. So we got f of x is equal to x over 1 plus x squared, and our domain is positive. Okay, same idea. We're going to call f y. Okay, now we want the inverse, so instead of y, we want x. So let's do a little cross multiply there to get rid of the fraction. Okay, just took that over. Let's take everything over to one side. Okay, don't let the two variables scare you. We just want to solve for x. Okay, so x, right, minus b plus minus roots, you know, all of that. Okay. So we've got this. Now again, this is plus minus. We need to see which one we're going to pick there. Right, that depends on our domain, right? So this is x, right? So they must match up with this. So plus or minus? Plus, yeah. We want it to be positive. Okay, we got that. Right. Any questions for this one? Oh, good. Okay. So the next thing on the list was continuity. 52.5. So we've got continuity, approximating errors, and tangents and normals. Yeah? Not given that? Restriction. What restriction? The domain. Domain's always given. Remember, to find the inverse, you have f from x to y. I have to give you the domain and range to give you the function. Yeah, no, domain's always given. I have to give it to define the function. Yeah.
Sorry, so I have to do the
The two.
what?
Two. Yeah. Any other questions? Yeah.
Can you go back to the third one?
The third one. The one where I asked, are there any questions? Okay. Yeah. Because if you find the domain of this thing, here's the domain. from 0 to 1. The natural log is negative. So you put the minus in front. This will make it positive. This part over here, it would be negative. This is not part of the domain. Yeah. So that would be like a follow-up question. Find the domain. Yeah. So you would say the domain is from 0 to 1. Yeah. But for these problems here, if I just say find the inverse without mentioning finding the domain or range, you don't need to do that. All right. Any other questions? Okay. So the stuff we still have to do. It was the continuity, was the next highest voted thing, approximating errors, tangents and normals, and rational function sketching. You want to carry on now or save it for tomorrow? Carry on. Cool, let's go. Okay, because when half the class gets tired, I'm just wasting my time talking, right? So, you all good? Okay. Where was that energy weeks ago? You all got energy now, and then weeks ago, half asleep. Okay, continuity. Yeah, well, a little bit better than my second years. We did our revision, and only 20 out of the 62 showed up, so a little bit better than that. Okay, continuity. So we've got a few problems here on continuity. So number one, we've got our function f of x is given by ax plus 5. We don't know what a is, some number a. Okay, if x is less than 2. If x is less than 2, and it will be x squared minus 1 if x is greater than or equal to 2. Okay, so a piecewise function, a, we don't know, we need to figure that out later. And the question is, find a such that f is continuous at x equals 2. Okay. So very similar to what we had in the test. Right, you got a piecewise function. We want it to be continuous, or we want to check it's continuous. What do we need to do? Left limit equals right limit. Exactly. So if left limit matches right limit, we know it's continuous. If it doesn't match, it's not continuous. So here we want it to be continuous. So let's check what the left and the right are and make sure that they agree. Okay, so if we're coming in from the left side, it's going to be 2 minus. Which one do we use for the limiting case? The first one. That will be from the left. Okay. Now there's no issues with the limits, right? There's no discontinuities, nothing like that. We can just put the 2 inside. Okay. It's just a straight line. There's no issues with the limits. What about the right limits? So now it will be 2 plus because we're coming in from the right. So if it's greater than 2, we better be using this bottom one here. Okay, again, parabola, no issues with the limit there. So it will just be 4 minus 1. We get 3. Okay, now we want this to be continuous, so these better match up. Yeah. So we get a single answer. So that will be our value of A. So if a is -1, it will be continuous. If a is not -1, then we're going to have a what kind of discontinuity? Jump, exactly. Right, that might be a follow-up question, you know? So here we got this value of a. If a is not -1, what is the name of the discontinuity? Jump. Okay. Any questions for this one? Okay. Number 2. Determine a piecewise function f such that x cot x is continuous on -pi/2 to pi/2. So in the previous question, we had continuity at a point, right? Just a single point here at x equals 2. Over here, we're now looking at continuity on an interval. Okay, so remember the definition for that. A function is continuous on an interval if it is continuous at each point on the interval. Okay. So we want this function here, x cot x, to be continuous on the whole interval. So somewhere on this interval, this function or this equation here is not continuous. Okay, we want to fix that. So at -pi/2, is there an issue? Right, you need to check the endpoints somewhere in between. Check on your calculators. There's an issue. What's the issue? Sorry? Doesn't exist. So we got an issue there. Okay. What about at B, the other endpoint? Also doesn't exist. Okay, so we've got some issues that we need to fix there. What about at 0? Check. Doesn't exist. So we need to fix those 3 points. So at A, at the one endpoint, at the other endpoint, and at 0, there's some issues there. We need to fix that. So -pi/2, 0, and pi/2. Okay. So what's the definition of continuity? There was that equation. You put in a big box. What's that? Okay, that's part of it. That's for the limit to exist. And then the second part. Sorry? Yes, function must be defined at the limit point. Good. So we need to do that for these 3 points. So let's check. So number 1, we want the limit as x goes to -pi/2 plus, because we're coming in from the right. Yeah. So we want that. So we're going to take the limit as x goes to -pi/2 from the right. This better match up with the function value. Okay, so what can we do here? What's the issue with this limit? We can rewrite it slightly. Hmm? 0 over 0. No, the bottom's not 0. The top is fine. It's pi over 2, minus pi over 2. That's fine. What happens in the bottom when we take the limit? No, not undefined?
It's unknown.
Yeah. So if you have some constant over something that's unbounded, what do we end up with? 0. Good. We get 0. Yeah. So we take the limit, we get 0. Number 2, limit x goes to 0. Now we need to be careful. We need to do from both sides. So let's go from the left side. Okay. So what's the issue here?
Sure.
Zero over 0. Yeah, we can write it like this. Right, we get 0 over 0. Okay, good. So if we have a limit with something 0 over 0, what can we do? Someone said? L'Hopital's rule. We just get 1. Okay. You can do the same thing for 0 plus, you also get 1. So at x equals minus pi over 2, the function better be 0. At x equals 0, the function better be 1. And lastly, you need pi over 2. Okay, so let's see what this limit gives us. So the top part will be pi over 2. That's fine. What about the bottom part? Sorry? Unbounded. So we have pi over 2 over infinity. What's that going to give us? 0. Good. So these were the issue points here. So how do we make this continuous? The limit must equal the function value. So f is continuous at x equals a if the limit, which we've got now, we've got these limits, equals the function value, which we now need to do. Yeah, so we're going to split it up into these 3 parts here, and the bits in between that we left out. So when x equals minus pi over 2, should be 0. Then between minus pi over 2 and 0, there's no issues. It's continuous. Okay. What happens at 0? What was the limit at 0? 1. So it should be 1. Okay. And then between 0 and minus pi over 2, there's no issues. So we can just leave it like that. Okay. And at pi over 2, we said that the limit was 0. Okay. So we get this function here. What are these points called? What type of discontinuity was here? Sorry? Yeah. What type of discontinuity? Not jump? Removable. It was removable discontinuity. Okay, because at 0, we have something like this. There was an open circle there. So the limit from the left, that gave us 1. The limit from the right gave us 1. But at 0, there was an issue. But we can remove that discontinuity by defining the function to be 1 here. So the circle becomes closed. So it's a removable discontinuity. All right. Any questions for this part? Okay. Last one here on continuity. Prove that the equation cos x equals x cubed has at least one real root. So we've got this equation here. We want to show that there is at least one real root. We don't know what it is, but we want to show that there is at least one. Okay, now cos x, is that continuous? Yeah, of course it's continuous. There's no issues there. X cubed, is that continuous? Yeah, they're both continuous. So what if I did this? If I have two continuous functions and I take their difference, is that continuous? Yeah, we proved it. Right? The sum of two continuous functions are continuous. The difference is continuous. The product is continuous. We showed that earlier. Okay, so if we were to sketch something like this, we know that it's continuous, so we can draw it with one continuous line, right? Continuous. We're going to have something like this. It's one continuous line, right? It's continuous. So what we want to show is that there's this point here where x is, at that point x, where the function value is 0. If the function value is 0, it means that these two must be equal, which is what we wanted to show. So over here, is there such an x that does that? Okay, so the goal is to not find this x, but just to show that there is this x. What can we use to show that? Yeah. Right, so it does something like this. We know that. So we just want to show that at this point, whatever it might be, this function value takes the value 0. Okay, how about we make it a little bit interesting? Whoever gets it gets 5% extra in the test. First person to put their hand up with the correct answer. Yeah. No. Yeah, in the back. Sorry? No. Yeah, you had your hand up next. Yep. Sorry? Yeah, well done. Did your student number? You did that extra powerful sentence test. Yeah, intermediate value theorem. So what we're going to do here is look at some value over here. Let's call it A. Any A, somewhere over there. We're going to look at some B over here. And we're going to look at the function values for those two. So at x equals a, we have f of a, and at x equals b, we have f of b. Right? We just picked a and b on either side. So if we can show that f of a is positive and f at b is negative, it means somewhere in between it must be 0. It's continuous. You can't go from positive to negative without going through 0. Okay, so if we can show f of a is positive and f of b is negative, then how do we get from a positive number to a negative number? You must go through 0. Right? There's no other way. If you start drawing from the top and you draw a line to the bottom, you have to cross the axis somewhere because it's continuous. You have to cross the axis. Okay, so now the goal is, what are these values? So we just think of some values, sub it in, see what we get. So we've got cos x minus x cubed. So let's think of a nice value for a. So 2. Try 2. What do you get? I mean, cos of 2 is not so nice, but you can try it. So let's say a is 2 and b. Where'd the 2 guy go? Oh, we got a is 2, b is? Okay, we need someone else. Pick a number. Hey, picking a number is not so difficult. Okay. Yeah, check 2. What do we get? Negative 8.42. So that's f of x. So if x equals 2, we get that. Let's check something after 2. And if it's still negative, we need to then pick something less than 2. Remember from your tutorial assignment. Okay, so let's pick something larger than 2. See if it's still negative. It is still negative. Okay, so that's not going to help us. Let's pick something less than 2. Yeah, 1. That's a good idea. Still negative. Let's pick something smaller than 1. 0 gives. That's fine. That will do the job. So at x equals 0, we got a positive value. At x equals 2, we got a negative value. So somewhere in between, it must be 0. So x equals 0 gives a positive value. X equals 2 gives a negative value. So that means somewhere between those, we don't know what it is, it must give 0. And in that tutorial assignment, you did exactly this, right? You started with one value and another value, and you looked in the middle to see where it changed sign. That's exactly what we're doing here. But here we only need to do one step, right? We're not interested in what the value is. We just want to show that there is some value. Okay, so if you want to define this x value, you would then look halfway between and repeat the process again. Here we don't need to do that. All right. Any questions for this one? All good. Okay. Let's have a look at the next bit. Any questions on the limits and continuity before we move on? Okay, remember limits, limit laws, continuity, all those proofs. Any issues? Yeah. The graph. You don't need the graph. This is just a picture to show you what's going on. All of this is just on your calculator, checking the values. Yeah. All you do is you pick one value, like the 2 guy, you pick 2, pick something more than 2 and check, pick something less than 2 and check. I mean, you could have started with anything. It doesn't really matter. Okay. I mean, don't pick like 200. You're going to be, there all day. But just pick something and you can check. Right. Any other questions? Oh, good. All right. So nothing on continuity. You're happy. Okay. Next bit. Okay, I think we'll finish the approximations and errors, and then the tangents and normals, and the sketching. We'll have to do that tomorrow. We got like 15 minutes left here. Yeah. Yeah, proofs. Yeah, they might be in the test. Oh, not the June test. Yeah. No. Remember, class test 2 is from L'Hopital's rule onwards. Yeah, no, not the limits. So limits, obviously, with L'Hopital's rule, but continuity, that was class test 1. So that might be in the June test, that's class test 1 and class test 2. And definitely in the final exam, proofs. At least 20 to 25% of your final exam is proofs. Okay, seen and unseen. Okay. Any other questions? Oh, good. Okay. Next bits, approximating errors with differentials. Yeah. So again, it's just some word problem. We want to estimate the error. So number 1. The edge of a cube was found to be 30 centimeters. With a possible error of 0.1 centimeters. Right. The word problems, it's always something like this. You've got some measurement, some error. We want to find estimate the other error. Use differentials to estimate the error in calculating the surface area. Calculating the surface area. Okay, so it's always similar to this word problem here. Okay, so we want the surface area. Let's call it A for area. What's that going to be for a cube? 6x squared. Okay, so we got some cube, side length x. We got 6 of the faces, so 6x squared. So we want to use differentials to estimate the error in the surface area. So delta A, that's going to be the derivative delta x. It's always the same sort of thing. So x, we know what that is. That's 30. Delta x, that's 0.1. So let's put that in. Okay, you can check what that is. What's that? 36. Okay, and then the units. So it's going to be the surface area in centimeters, yeah? So centimeters squared. Yeah. Any questions for this first one? All good. Okay, number 2. Use differentials to estimate the amount of paint needed to apply a coat of paint. 0.05 centimeters thick. To a hemisphere with diameter 50. Okay. So it's a hemisphere, so half of a sphere. So we want the area of this, okay, times a little thickness. That will give us the amount of paint. All right, so something like this. Okay, so you've got a hemisphere. There's a little thickness to the paint layer, 0.05. Okay, and that's going to be all the way around here. Okay, so we see that in terms of the radius here, it adds a little delta R to the radius. So you had some initial radius, then you put the paint on, so it's R plus delta R. And then this little bit here, delta R. Yeah. So we want to work out that volume, that pink volume there. So we have the volume. What's the volume of a sphere before we cut it? So that's the full one, right? Okay. But we just want that top part. Okay. So what's that going to be? 2/3. Yeah. Okay. So that's just for the top part now. Okay. Please remember to cut it in half if it's a hemisphere. So we want this dv, that's the little extra bit that we've added on, delta v. So it will be 2 pi r squared delta r. Right, you just do the derivative. So this is what we know. The diameter is 50. Okay, but here's the radius, so we need to be careful with that. Okay, and then the delta r, we said that was the thickness that we've painted on, 0.05. Okay, and then the units, well, it's the amount of paint needed, so this will be centimeters cube. Okay, again, you can simplify that. 2 decimal places should be fine. If it's like 0.00 something, you can do 3, but 2 decimal places should be fine. Okay. Any questions for this one? Oh, good. Okay. Last one here, number 3. The radius of a sphere is 9 meters. with a possible error of 1%. Find the percentage error in measuring the surface area. So it's the full sphere that we're looking at, not a hemisphere. So A equals what? 4 pi r squared. Okay, please remember, these will not be given to you. You have to know your volumes and areas and all of that. Okay, you expected to know that already. Okay, so we want the error in this. So that's delta A. Okay. But we don't want it just like that. We want it as a percentage error. Sorry? What do you mean 0.01? No. We have to divide this by the total area and then times by 100. Right? Because it's the percentage of the total. Right? Like your math mark, right? You got something over the total times 100. It's like that. Okay, so if we have this as our relative error, then we just write that as a percentage. It's always the percentage of the total amount. So this is going to be 8 pi r delta r over 4 pi r squared. Okay, we can simplify this a little bit. So 8 pi over 4 pi, we're going to have 2. Okay, and then we can substitute. Okay, so delta r. That was the error in the radius. So it's 9 meters with an error of 1%. So it's 1% of 9. Okay, over the radius, we said that was 9. Times 100, that gives us our percentage. Okay, remember, percentages is always something of some total. Okay, again, you can simplify that, check your answer. All right, any questions for the differentials part? Okay. Okay, so there's just 2 more things, tangents and normals, and then the function sketching, but we'll save that for tomorrow. Okay, I think we only have this venue until 3. I don't know if anyone's coming after that. Right, any questions before we go? Okay, so we'll finish off tomorrow.